series and parallel resistance, and our overall goal is to be able to use this to help us simplify circuits so that we can later analyze more complicated circuits. All right, so let's start with series. All right, this is a picture of a single loop circuit. Three of the resistors are in series. All right, it turns out you can tell a resistors are in series if it's the same current flows through each one. All right, so I'm looking at this current, and I would reference this as I. Okay, and if I choose I in this direction, the passive sign convention would say I have to have this first voltage drop as plus minus V1. All right, I is still moving this way, so plus minus V2. I continues on plus minus V3. All right, so if I wanted to find I could write a KVL equation around this loop. Okay, so I'd start at the bottom. I have a rise of 30 volts. The rises are on one side, the drops are on the other. 30 volts is a drop of V1, right? Moving from here to here is a drop. Moving from here to here is a drop, so a drop of V2 and a drop of V3. For each of these, I know that Ohm's law applies. It's going to be I times 10 plus I times 15 plus I times, I didn't mean to use 15, I meant to use a different resistor, I times 5. All right, so from there you can use properties of algebra, pull the I out, and I would have 10 plus 15, which is 25, plus 5, which is 30. And I can solve for I. I is 1 amp. Okay, so let me move this down. We'll talk about parallel here in a second. All right, so it turns out that this 30 is an equivalent resistance for this circuit. So by that I mean, what if I had just a single loop circuit where here's 30 volts and I replace it with our equivalent? Okay, well, it's a real easy KVL, right? You have a rise of 30 is equal to the drop of the voltage plus minus V. And then Ohm's law says that's I times R equivalent. R equivalent is 30, so I can solve for I. All right, so what happens in practice when you start to analyze circuits is you see this circuit and you say, I see these three resistors in series, all right, 10, 15, and 5. Series resistance adds. So I just add 10 plus 15 plus 5, and I immediately jump to this simpler. This is a simplified circuit, all right? And from there, I essentially have memorized the answer, right? I normally don't write this step of here's a KVL, here's Ohm's law. I mainly apply for a simple circuit like this, V equals I times R. Okay, V is equal to 30 is equal to I times R equivalent. I can jump straight to the answer because I've seen it several times before. So I make the series equivalent, make the substitution into an equivalent circuit, and then I can solve for I. All right. Once I know I can move this back and find other things about the problem. Like if I wanted to know what V1 is, right? Because I already know what I is 1 amp in this case, then V1 is, according to Ohm's law, 10 times 1, so V1 is 10 volts. All right, V2, 1 times 15 is 15 volts. V3, 1 times 5, which is 5 volts. So notice this process. I simplify the circuit, find something about the circuit. In this case, it was the current I. The current I is going to stay the same between the equivalent circuits because as far as this voltage source is concerned, the laws of physics are the same between the series resistance and the equivalent circuit here. So this current is going to be found easier from the equivalent circuit, and then we move it back up to answer questions about the more complicated circuit. All right, so that's the basic idea. All right, so the next thing I wanted to do is talk about the same idea only with parallel. All right, so with parallel, I'm going to start looking at a current source. All right, you don't have to use a current source, it's just easier. All right, so there's a current source, and we're going to connect basically the current source to an equivalent resistance. All right, isn't that a simpler circuit? If I wanted to know the voltage, V, this would be 6 times R equivalent. V is 6 times R equivalent, because I is the current, V equals I times R. And I could solve for this voltage, V, across the equivalent circuit. All right, so that's where I'm heading. The first thing I wanted to do, though, I've looked at circuits for a long time, so things are more obvious to me than they will be for you when you first start out. Is it obvious to you that this circuit is the same? Okay, so I'm going to connect with curved lines here. 75. My thing straightens out. $50. 30. These are in ohms. We only really need 2 points to connect between. And so this would be point A on the bottom of this, point B on the bottom of the circuit, and point A on the top. So I can, if there's just wires connecting, I can shrink those wires down to a single point. All right, and I think that makes it more obvious, I'm hoping, that we have currents flowing through here, I1, I2, and I3. And if I do a KCL at this node A, what do I get? The current going into the node is 6. The currents going out are I1 plus I2 plus I3. That is not as obvious in this circuit. So I made the mental adjustment of collapsing these points that are distributed in space just to make it easier to draw a squared up looking schematic to how these are really connected. They're connected at single points. All right, and from here I think it's easier to tell this is this current coming out of this node this way, and then the current going into the node is here. Okay, from there, what I notice is that for parallel resistance, these are all connected across the same voltage, and that's the difference between series and parallel. Remember, for series resistance, all the resistors had the same current running through them. For parallel, it's a little more complicated. It's the same voltage. And remember, voltage doesn't run through elements. It's across. All right, so it's the same voltage across each element, right? If you wrote a little loop equation, let me get rid of these. I'm trying to help you see this, because once you see it, it's obvious, but like I say, nothing's obvious till it becomes obvious. All right, so if I wrote a loop equation here, here's a loop, okay? What do I have? I have the voltage across the 75 ohm resistor. I have the voltage across the 50 ohm resistor. I have a rise of V75 moving from here, moving this tray. There's a rise of V75, and if I keep going around that loop in this direction, I have a drop of V50. So what I know is V75 is the same voltage as V50. And in fact, it's voltage V that we've labeled before. All right, so I'm trying to draw the point that it's the same voltage across each one. That's harder when you're first looking at circuits. It's harder to see. Okay, well, once I know the voltage, I'm going to call that voltage across each of the elements as V. All right, once I know that voltage, I can calculate each of the currents because it's Ohm's law. Okay, so I1 is V divided by R1. Okay, so R1 was 75 ohms. Okay, I2, let me move it like this. Okay, I1 is V over 75. I2 is the same V, that's the whole point, it's parallel voltages. The same V divided by 50. I3 is the same V divided by 30. Okay, I can pull this out and I get that 6 is equal to V, and I move this over, right? Pull out the V, I have 1 over 75 plus 1 over 50 plus 1 over 30. Okay, so if I solve for V, V would be the current 6 divided by, I'm going to write over here, hang on, 6 times 1 over 75 plus 1 over 50 plus 1 over 30. All right. Well, this would be 6 times R equivalent, right? So going all the way back up to where we were looking at equivalent circuits, all right? V is equal to 6 times R equivalent. That's right here. All right, we've got that in that form, and now we can spot what R equivalent would be. R equivalent is this. All right, so essentially we just derived the formula for R equivalent. Okay, if you had 3 resistors in series, it would be 1 over R1 plus 1 over R2 plus 1 over R3 inverse. Okay, what if you had 5 resistors in series? It's going to be 1 over R1 plus 1 over R2 plus ... 1 over Rn. Okay, so N resistors in series, inverse. All right, so that's equivalent resistance for parallel combinations. All right, well, how does this all work? All right, let's do a simple circuit analysis problem. I'm going to draw a voltage source here. Let's make it 60 volts. Let's have a resistor here, a resistor here, a resistor here, and a resistor here. Okay, let's make this 20 ohms, 20 ohms, 5 ohms, and 15 ohms. All right, so what I would like to do is use the ideas that we've talked about to solve for this current I. Okay, and so this is not easy. This is going to take you a while to be able to see. Let me give it a little more space here. But I'm looking at this and I'm thinking, I'd really like to simplify this circuit. Okay, one of the things I can do is I notice it's the same idea before, that these really are the same thing as having a single point connected. Right, and I could join that like that. I'm not sure if that helps you, but if I looked at this and I marked this plus minus V, it's the same voltage across each of those. All right, so I'm looking at this and I'm thinking, the things I'm highlighting in blue, those were in parallel because they have the same voltage across them. Okay, and then I'm also looking and I'm thinking this current I, it's the same current flowing through both the 5 ohm resistor and the 15 ohm resistor. So I'm going to highlight those in green. These two have the same current flowing through them, so those are in series. Okay, so let's take this in steps. All right, let's redraw the circuit. And I can replace the two resistors that are in series with their equivalent. So that would be, series resistance add. So this would be 5 plus 15 is 20 ohms. Okay, and I can also replace the parallel resistors with their equivalent. Okay, so that'd be 1 over 20 plus 1 over 20 inverse. Okay, so you can check this on your calculator, but that turns out to be 10. Okay, that's looking pretty good. All right, but then I look at it one more time and I'm thinking, again with the series resistance. Okay, so I can make another equivalent circuit. And have this be 10 plus 20, which is 30 ohms. Okay, and now we know 60 is equal to the current I times 30. All right, so I is 2 amps. All right, so we immediately got that. And this applies way back over here into this circuit. 2 amps is flowing through this circuit. So if I had wanted to know what the voltage across the 15 ohm resistor would be, well, what is it? All right, that's a quiz question for you. All right, it's just, the current through it, and it's Ohm's law that applies for this voltage. I'm going to call that V alpha. So the quiz question is to solve for, there's no alphas in the quiz software. Let's call this VA. Okay. All right, so there's an example of using equivalent circuits. We're going to do some that are a little more complicated. Sometimes it's hard to see parallel and series. My experience is that it takes you a while to see this, and some of you see it right away, and some of you, it just takes a little bit of looking at it, and then once it clicks, it clicks. It's not too bad to find how to find equivalent resistances.